Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 20th, 2025, about 2 days ago. It shows that a multi-fingered robot hand can learn closed-loop manipulation skills purely from in-the-wild human demonstrations captured with smart glasses, reaching up to 86% success on everyday tasks without any robot interaction data, simulation, online corrections, or reinforcement learning. The paper is titled Dexterity from Smart Lenses, Multi-Fingered Robot Manipulation with In-the-Wild Human Demonstrations. And as we will see later, the implications for how we train dexterous robots are pretty dramatic. Alright, Figure 1 lays out the full pipeline, which turns casual human demonstrations into robot skills. The left panel shows in the wild data collection with Aria Gen 2 glasses that capture hand pose, high-resolution color, and stereo depth, while people manipulate objects anywhere. The middle panel illustrates a single in-scene demonstration in the robot workspace. The right panel then depicts the learned policy driving a multi-fingered robot hand to perform the same tasks autonomously. The previous figure sketched the pipeline, and Figure 3 now positions this method among prior human-to-robot learning frameworks. The left panel indicates which approaches truly work with in the wild data, highlighting that only a few, including this method, qualify. The middle chart compares available sensory modalities, showing that this work uniquely combines color, depth, and three-dimensional object and hand tracking. The right chart contrasts embodiment, where this method occupies the rare quadrant of human data paired with dexterous robot hands. So, while Figure 3 compared this approach to prior work, Figure 4 dives into how the system actually functions end-to-end. The left side shows data collection and processing, where smart glasses track objects in 2 dimensions and estimate depth from stereo slam cameras to build 3-dimensional scenes. The right side presents point-based policy learning, which feeds object points and fingertip locations through a transformer-style network. That network predicts joint angles for the robot arm and hand, so the robot can reproduce the demonstrated manipulation on real hardware. Alright, while Figure 4 focused on architecture, Figure 6 showcases what the learned policy actually does on real hardware. The montage presents 9 everyday tasks, with each row showing the robot hand progressing through a rollout. The leftmost grids summarize success, partial success, and failure across many start positions. The final panels report trial counts, like 13 out of 15 for toaster pressing and toy picking, highlighting strong, but not yet perfect reliability. Well, Figure 6 showed the raw rollouts, and Table 1 now quantifies how different training recipes affect success. The table compares 5 datasets on toaster pressing and toy picking. Using only in-scene data reaches about 30% and 10% success, while using only in the wild data completely fails. Mixing in-scene and in the wild demonstrations during both transformation and training jumps success to roughly 86% on both tasks, which underscores how crucial that combined recipe is. So the big takeaway is that casual human videos from smart glasses, plus a single in-scene demo, already let a dexterous robot hand learn robust closed-loop skills without any robot trial and error. This hints at consumer-style telepresence. Anyone recording daily tasks could one day teach home robots. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.